Welcome to statistics class, and our topic for today is analysis of variance. So what is ANOVA? So it is the testing the hypothesis about the mean is not only possible in single or two sample groups. So generally, several sample groups coming from several populations taken into comparison may come in a common scenario. So for the instance that several sample groups are compared, we can competitively apply a t-test. In our previous study, t-test is the test for two groups, but this will inflate the probability of committing a type 1 error. So instead of doing multiple t-tests, we can use a testing method which is called the analysis of variance ANOVA or F-test. So if you want to test the difference for three or more groups, we will use analysis of variance or ANOVA. While generally the t-test is intended for at most two groups of samples, ANOVA can also be applied for two samples. This is because the t-test directly related to the F-test or ANOVA test, since F is equal to t squared for single treatment degrees of freedom. So in addition to the possibility of the inflated probability of committing a type 1 error for t-test analysis on cases where more than two groups are being compared, the t-test is also not appropriate if the interaction effect between and among variables is also measured. So generally, this makes ANOVA as the more appropriate tool for testing the equality of means of several groups. Always remember, we will use ANOVA for three or more groups. So, single factor analysis of variance. So, the following assumption should be considered in using analysis of variance. So, the variable under study for each group or your sample must come from the population where such a variable is considered normal or at least normal. So, we have to test for the normality test before we can use the analysis of variance. And then another assumption, the population variances are assumed equal. And then the data are independent of each other. So in performing analysis of variance, the total variability of the scores or data is usually partitioned into two sources. One is the variability of the values within groups, and the other is the variability of the means between each group or sample. It is a common practice in analysis of variance that the computations leading to decisions are summarized in tabular form, or doing so will make it more fitting to partition the total variability of the data. It will be discussed further later with our example. So to summarize, here is the four assumptions of analysis of variance or assumptions of ANOVA. Number one, homogeneity of variances of the experimental errors or heterodidacticity. And then the most, it's important one, the normality of the distribution of experimental errors. And then three, independence of the experimental errors. And then the fourth, additivity of the treatment effects and environmental effects. So, what is this homogeneity of variances? What are the causes of violation? Since it is assumption before we could use the ANOVA. So some treatments are erratic in their effects, or there's a presence of outliers. It's not that similar. The variance is not, there's a greater uh, noticeable values, so outliers, and then non-normal or skewed distribution of data. And then how to detect? How to detect variance heterodidacticity. Number one, for each treatment, compute the variance in means across replications. And then two, create a scatter diagram of the mean or your x and your variance y. And then visually examine the scatter diagram to determine the pattern of relationship. Let's see this one. How to detect variance heterodidacticity with a graph. So here, homozydastic, and then here, heterozydastic. And then there are tests to test for homogeneity. We can use the Hartley's Fmax test, Bartlett's test, Leven's test, Brown-Forsyth test, Bach's test, and others. But the commonly used test is the Bartlett, the Leven's, and Brown-Forsyth test. So, next assumption is normality. So, experimental error is appropriately normally distributed when the sample size are adequately large. So, what is the violations? Extremely skewed distribution. So, the test for normality, we could use the chi-square goodness of fit, or we could use the Kolmogorov-Smirnov test, the Wilks-Shapiro W test, and normal probability plots. And sometimes this is also already projected or presented if you have or if you use the computer aided or software to test for your normality. And then another assumption is the independence of errors. So responses on neighboring plots tend to be correlated. So if you have the replication one, and then it is correlated to another. So independence of errors is violated in experiments where the experimental units or replications are arranged systematically. That's why we have the randomization to control this error. And then the remedy is proper randomization of treatments to the experimental units to give independent errors. So test for independence, we could use the Durbin-Watson test or Run's test. And then a fourth assumption for ANOVA, we have the additivity of effects. So treatment and environmental effects do not interact. And then multiplicative effects or non-additivity is common in disease studies where the effects of pathogens are usually multiplicative rather than additive. So that's why if you are conducting your experiments, so environmental effects should not interact or should not have an effect to the performance or to the yield of your treatment. So the effects of treatments across blocks are not uniform, and the effects of blocks across treatments are also not uniform. So there are logarithmic transformation and other data transformation that will convert the data to have additive effects. So we'll go now to the computation, or what is this analysis or one-way analysis of variance. So here is the basic parts of one-way ANOVA table. So whenever we have the test of hypothesis, we have to present this table. So table 1 example, analysis of variance SV, and then DF, SS, MS, F computed. So SV is sum of squares. And then DF is the degree of freedom. And then MS is the mean square. And then FC is the F computed. And then F alpha DFTR, comma DFE is what we call the F tabular. And then under the source of variation, we have the treatment, the error, and the total, which is we will find or we will compute for the value of each, and we will have our conclusion for our experiment. So here is the computation of one-way analysis of variance table. And it can also, if you need a detailed example and sample computation, please look at our textbook, page 13 to 17. So always remember that there is a different computations or formula for the different experimental design. For example, if you use the CRD, then you will also have a different computations for the CRD and then for the RCBD. But still, they are similar. So how to compute for the DF treatment? It is number of treatments minus 1. So number of treatments are the factor levels. So if you have factor levels of 4, then minus 1, then that would be your DF treatment. Then you put that one here, DF treatment. And then DF total is the N minus 1, or the number of your replication multiplied to your treatment minus 1. That would be your DF total. And then for your DFE, that is DF total minus DF treatment. And then the first one that you should compute is for the correction factor. So correction factor is equal to the grand total. So the value, so the total data values that you have, and then you square it over your N, or your samples, or your treatment times your replication. For example, you have 4 treatments and then you have replicated it 3 times, so you have the total N 4 times 3. So that is how you should compute for your correction factor. Grand total, then squared, divided by your N. And then for total sum of squares, total SS, it is the summation of the squared of each values minus the correction factor. And then for your treatment is SS, it is equal to the summation of your squared treatment or total treatment in each treatment levels divided by number of replications. And then the error SS is equal to total SS minus the treatment SS. And then how do we get the treatment's mean square? That is treatment sum of squares divided by the DFTR, or your DF, degrees of freedom treatment, or the number of treatment minus 1. Remember, this is our DF treatment. So when we get the treatment mean square, it is equal to the treatment SS divided by number of treatment minus 1. And then for the error mean square, that is error sum of squares that we have got from here, divided by the number of treatment multiplied by the number of replication minus 1. So this is how we compute the DFE. And then for the computed, we have the treatment mean square divided by error mean square. And then we need this computation, or how we get the F tabular value. How would we know that our study is significantly different from each other, or we have to reject the hypothesis, or fail to reject the hypothesis? So we need to know how to use the F tabular value. So in our textbook, you can see that in Appendix E, or in page 635 in our textbook. So for example, we have the level of significance of 0.01, and then our computed DF error is 5, and then DF treatment is 3. Then at 5%, we have the F tabular value of 5.41. So this is the FTR here in the column, the FTR, and then on the horizontal, here we have the 5, the FE. So in the intersection, the values of that is the 5.41 is for 5%, and then the 12.06 is for 0.01. Always note of the instruction that 5% or 0.05 level of significance is light type here in the upper part, and then 1% or 0.01 level of significance we have here in the boldface type. So let's have some example for you to better understand it. Test of hypothesis. So for example, we have the yield or tons per hectare of corn applied with different nitrogen levels. So we have the 30 kilograms per hectare, and then 60 kilograms per hectare, and then 90 kilograms per hectare. And then it was replicated, our factor levels is replicated 4 times. And then this is the data. So in 30 kilograms per hectare, replicated 4 times. Replication 1 is 5.6, 4.0, 3.4, 4.6, and then our total, this is the treatment total, 17.6, and then the treatment mean is 4.4, 4.4. And then 60 or 60 kilogram per hectare is another treatment level or factor. Then the total is 20.2, and then the mean is 5.05. And for another treatment factor or levels is the total is 22.2 and the mean is 5.55. So our statement of the problem is, are different nitrogen levels more effective than the other levels? So we need to conduct a hypothesis testing for this if we want to find out if there is effective or there is a different effectivity for each level. So the objective is to determine if there is significant differences in mean yield among the different nitrogen levels. So if you want to know that if I will apply 30 kilograms per hectare, will it be similar? Will I have a yield similar if I put 60 kilograms per hectare or I put 90 kilograms per hectare? So we have to conduct a hypothesis testing. So always remember that the test of hypothesis testing, we have to follow these 5 basic steps. Number 1, state your hypothesis. So as discussed in our previous slide, in our previous lesson, HO is our null hypothesis and then HA is our alternative hypothesis. So when we state the null hypothesis, we have to state it this way. Mu1 is equal, to represent our factor levels 1. Mu2 is equal to mu3 is equal to mu. So state it this way in the textual form. There are no differences in the mean yield among the different nitrogen levels. So in other words, if I use the 30 kilograms per hectare, 60 kilograms per hectare, 90 kilograms per hectare, their yield is just the same. So that is our hypothesis or our null hypothesis. And then for our alternative hypothesis, we will use at least one mu1 is not equal to mu, or I is 1, 2, 3, because we have the 3 treatment levels, or at least one of the nitrogen level has a different mean yield. So step 2, we have to state our level of significance, which is our alpha is equal to 0.05 or 5% error. And then we have to state our test procedure. So we will use the F test. And then the test statistics, if you are presenting your answers or for your computation, just show your ANOVA table. Follow the similar table we have discussed in the previous slide. The computation or the F computed is equal to MS treatment divided by MS error. So what is this test statistics based on our example? We will compute for the correction factor. So again, it's grand total, you square it, divided by n. So we have the 3 treatment levels, the 30, 60, 90, and it was replicated 4 times. So our samples, 3 times 4, we have 12. So for our correction factor, we have 60 squared divided by 12 equal to 300. And then another, we have to compute for the total sum of squares. So in other words, each values, we have to square it and then add everything. Okay? Minus 300 is equal to 9.4. So our TSS is 9.4. And then for our treatment, sum of squares, we have to compute it. Summation of yi total squared over replication of each factor level. So in our case, the 30 kilograms per hectare, where there is a total of 17.6. So you have to square it divided by the number of replications. So 4. And then for the 60 kilogram per hectare, we have 20.2 squared and then divided by 4. And then 22.2 squared divided by 4 minus our CF or correction factor, which is 300. So it is equal to 2.66. And then for the error sum of squares, just subtract the TSS minus the treatment sum of squares. So it is equal to 9.4 minus 2.66 is equal to 6.74. So another one, the mean square treatment, again, treatment sum of squares divided by the T minus 1 or the treatment level. So we have 3 minus 1, that is 2. So 2.66 divide 2 is equal to 1.33. And then another one is our MSE, or mean square error. So it is equal to error sum of squares or sum of square error divided by n minus t. So our error sum of squares is equal to 6.74 divided by 9 is equal to 0.74. 9. So here is our ANOVA table and input. Put your answers or calculation to this one. Always remember, for our decision rule, we have already computed, but how could we conclude that there is significant difference on the performance of our treatment levels? So note, if we are using tabular value or manual computations, we have to follow this decision rule. It is constant or it is fixed. So reject HO if F computed is greater than or equal to our F tabular. How do we find this F tabular? 0 point alpha, this is DF, and then DFE. Else, fail to reject HO. And then another one, if we are using software-aided analysis, we have to use the p-value, or if we are using star, we have to use the p-value or the probability value. And this is our decision rule that we have to follow. Reject HO if p-value is less than alpha. Our alpha is our level of significance, either 5% or 1%, and then or for 5% that is 0.05, and then for alpha 1% we have the 0.01, else fail to reject HO. So let's show, we have to present it in our step 5 critical region. So again, this is fixed. Okay, this is our decision rule. Reject HO or reject the null hypothesis if F computed is greater than F alpha, that is level of significance, DFTR, that is our DF treatment, and then DFE, that is our DF error. Then where F computed, as we have compute in our based on our data, we have 1.78, and F tabulated F 0.0529 is equal to 4.26. So where do we find this 4.26? Since our alpha is 5%, so based on our table, we have the DFTR treatment, which is 2. So in this column, we will use the 2, the second column, and then the DFE, which is 9. So intersection, this is our F values or F tab values. For 5%, we will use 4.26. If we are using alpha 0.01, then we will use 8.02. But in our case, in our example, we are using the alpha 0.05. So we will use the 4.26. So this is how the F tab is here, 4.26. So based on our decision rule, that we will reject HO if F computed is greater than F tab. So in our case, since 1.78 is less than 4.26, so our decision or our conclusion is hence fail to reject HO because it is less than. Okay, so this is fixed. Just change the value here for F computed and then F tab, then have your conclusion. And then for our decision, we have failed to reject HO based on our analysis. And then for our conclusions, there are no, you have to check your null and alternative hypothesis and state it this way: there are no differences in the mean yield among the different nitrogen levels. So if we are using a star software or we are using the computer aided analysis. So always remember that before you use your data to your star folder, be sure it's in CSV or comma delimited before you save it. So in my case, I have a data or folder as agribio example data 1. So you can use any file name, it's up to you. So then it will be imported to my star software. So here it is, and then it was projected. So an example how you encode data in your Excel and how it looks in star. So you just arrange the nitrogen levels here, 30, 60, 90, and then replication 1, and then you put the value or the yield. So for nitrogen level 30, and then replication 1, it is 5.6. So on and so forth. Then after that, you have imported your data to your star. Then you click the analyze here in the upper part on the tab. Then can choose your analysis. So we will choose the analysis of variance. After that, we choose the or click the CRD or completely randomized design. So in our case, you are using the CRD. But if your analysis or your experimental design is RCBD, then you click RCBD. And also note that be sure to put variables in the proper box because sometimes it is placed in here, then you have to click it and add it in this box in response variable because our response variable is the yield. So we have to click here and put it here in the response variable box. And then for the treatment, the nitrogen level. Then after that, you click OK. So in our case, you have to state it this way again in the 7 steps. State your hypothesis. So similar, even if you compute manually, so they have the same or same state or hypothesis, HO, HA. So they are just the same. And then level of significance here, alpha, F test the same. And then test statistics, you just have to show your ANOVA table from your star analysis. You can copy paste it. So here example in this is projected in your star software. So you can just copy this one and put in your test statistics. But always remember, uh, here we can see here F value. Same with our F computed. If we can compute manually, they have the same 1.78. But what is projected here is not the F tabular based on your table or F table, but they projected or display the probability value. And also, the CV or the coefficient of variability is given in our analysis. So, if we are using the probability value, then we have to follow the decision rule for the probability. So, here in our case, same. Reject HO if, however, what changes here is the p-value less than your level of significance. So your level of significance is your alpha, the 0.05 or 0.01. But in our case, we use the 0.05. So always follow this decision rule. Reject HO if p-value is less than alpha. Where p-value is 0.22, where did it come from? So in our star analysis here, in PR or probability value, that is 0.22. And then our alpha, it is fixed 0.05. So here is our decision rule. We can only reject HO if p-value is less than. So in our case, our p-value is greater than our alpha. So hence fail to reject HO. So our decision is fail to reject HO, and there are no differences in the mean yield among the different nitrogen levels. Moreover, the CV is 17.31. So we come up to the same conclusions, which is to fail to reject HO. So before we end, I will read this text. Isaiah 26 verse 9. My soul yearns for you in the night. Yes, my spirit within me keeps a vigil for you when your judgment dawns upon the earth. The world's inhabitants learn justice. Yes, in life, even in analysis, we have to, we have the conclusion, the judgment based on our experiment as well as in our life. Always remember that there is a just God who watch over us. Again, thank you and God bless you, dear students. See you in our next topic.